Alright, so in this video I'm going to be explaining another important article about domain generalization, not domain adaptation, because in domain generalization we don't even have access to the samples of the target data. And we are using this adversarial network. So this paper in 2018 by University of Sydney and CMU. Domain generalization aims to learn a classification model from multiple source domains and generalize it to unseen target domains. A critical problem in domain generalization involves learning domain invariant representations. Let X and Y denote the features and the labels respectively. So under the assumption that the conditional distribution remains unchanged across domains, earlier approaches to domain generalization learned the invariant representation by minimizing the discrepancy of marginal distribution. However, such an assumption of a stable probability of your label given your features does not necessarily hold in practice. In addition, the representation learning function T is usually constrained to a simple linear transformation or shallow networks. To address the above two drawbacks, we propose an end-to-end conditional invariant deep domain generalization by leveraging deep neural networks for domain invariant representation learning. The domain invariance property is guaranteed through a conditional invariant adversarial network that can learn domain invariant representation. So this is just like other papers. We will see the distinction later. Suppose the feature and label spaces are represented by X and Y. A domain is represented by a joint distribution defined on X, the product space, X times Y. To simplify notation, the M's domain is denoted by P sub M, and the marginal distribution is. So in each domain, we have a sample domain which is drawn from P sub M. And we have a number of samples for each domains. So we first introduce this Jensen-Shannon divergence. It measures similarity among multiple distributions. And we use the marginal distribution P of X as an example to illustrate the general results. The Jensen-Shannon divergence among distributions is defined as the average of KL divergence of each distribution from average distribution. So this is the average distribution, which is shown here. It's just the average. And then for each of the domain, you go through and calculate the KL divergence between them. And again, you average them. And then this is a measure. This is a good measure. So a two-player minimax approach in this reference is proposed for learning a generative adversarial network and is proven to be equivalent to minimizing JSD between generative distribution and data distribution. So, in adversarial, we try to design G so as to fool the discriminator. The discriminator, for example, says it is from domain 0, domain 1, domain 2, domain 3. But the generator wants to fool that so that there is a kind of alignment between the distributions of these different domains. So we have multiple players. We extend. Now this is a contribution. We extend the two-player minimax to multiple players and prove its equivalence to minimizing the JS divergence among multiple distributions. Denote the distribution. So we are minimizing D, but we are maximizing over all domains. And D is the learn discriminator. This D is the learn discriminator that T of X comes from the M's domain. So it's just a multiplayer minimax game with this value function, because each game has a value function. But for our case, it's just the log of your discriminator. And we are summing overall distribution, all domains. So expectation from domain 1 plus expectation from drawing from domain 2. And so we are considering all of those things. That's why we say it's just the multiplayer games, because different domains discriminators can have different so instead of just one discriminator, they have like this: D1, D2, D3. For each domain, they have their own discriminator. And if you add the log of these domains, discriminators of T, then of course we have a generator T here, feature transformation. We call it a feature transformation. And then we try to fool the discriminator. So we minimize this T so that the maximization, so it's a minimax, but it's a multiplayer game. Then the rest of that is just theoretical in this paper. For example, let X prime for a fixed transformation, the optimal probabilities, you can derive it like this, which is very intuitive. And maximizing the value function pointwise and applying Lagrange multipliers, we obtain the following problem. This is our Lagrange multiplier. Because we want the domain to be 1, so this is our constraint. Another theorem: if U is the maximum value of your value function of this game, then U is, this is the proof that says that U is this. The existing methods proposed matching the marginal distribution across domain. However, the invariance of P of Y condition on T of X could not be guaranteed. Our approach corrects the changes in P by correcting the changes in P of X condition on Y. The conditional invariance is achieved by applying the minimax game to different aspects of distributions on the source domains, resulting in the class conditional minimax value and class prior normalized marginal minimax value. And we have this class conditional min-max value that I said. Class prior: if the sample size is not large, overfitting can easily occur in a deep network due to a very large number of parameters. As the number of examples in certain classes is sometimes small, learning with the above class conditional minimax value can result in overfitting. To improve the learning of domain invariant, we propose learning a class prior normalized marginal term that applies the minimax game value to all conditional distributions globally. So that equation shows that the marginal distribution is determined by the conditional distribution and the class prior distribution. The empirical version of class prior normalized is now this. So we have beta here. You see the network of architecture of the proposed methods. It has 4 parts. Feature learning. First we do feature learning, that T that I was talking about. Image classification network. In every task we have, for example, here the task is image classification. So it's a good framework for different purposes. And then we have class prior normalized domain, this class prior, which discriminates different domains with the loss that we explained. And also we have class conditional. Finally, we have this class conditional, which determines the domains for each image with that equation 13. So the class prior can be viewed as a weight of the log likelihood, because if you remember, it's like this one is like a weighted of what we had before, and so we can think about it like a weight of the log likelihood. So we introduced a conditional version of that. Everything is standard, but we are just using the conditional. We can implement the class conditional minimax gain, because we should respect the classes as well. If we have L classes, we must construct L sub-branches of the network. So we introduced the class prior normalized domain classification. This Y denotes the class label of the ith image of domain M. So we have this indicator as well. So we combine all the above losses, and this is what you get. The learning of the above loss can be separated into two steps. And a saddle point of the above optimization can be determined by performing the following gradient updates iteratively until the network converges.